Thank you so much. Network security, fifth lecture. So today we'll continue our lecture, and we're gonna introduce you to the modern symmetric key ciphers. Okay, we were talking about ciphers in the lectures. We started with the math background. We're building you up to this moment, and actually next class you'll talk about DES, one of the algorithms you used for a long time. So you will see exactly how it's built, but we cannot go there until you look at the small blocks, how we built the algorithms. Then you could put them together and you understand that. All right. So we're going to talk about the modern block ciphers, and we're going to talk about symmetric key modern block ciphers in this class. What do you mean by symmetric key? That means there is one key between the sender and the receiver. So what we have, try to take this here. So okay, so when you have a sender try to send a data to the receiver, okay, so they have to create a packet, right? A packet, they have to send it over the network, all right? So there is a key, so the packet in here, it has a data, you have to encrypt it with key, okay? This key is shared, KI for example, for the packet, is shared between the sender and the receiver, symmetric key, all right? Later on, we're gonna talk about public keys at a certain point of time. So we're talking about symmetric key where we have n-bit blocks. So usually you have a data, long data, whatever the data, okay, that's the data, okay, we divide it in blocks. So n bits, n bits, n bits, all right, and then you encrypt the block, you send it. The receiver will receive the block, decrypt it. You go to the next block, you encrypt it, send it, the receiver receives it and decrypt it, and so on and so forth. So we're trying to divide the data into blocks of data. All right? So there is two kinds. We're going to talk about, there is a block encipherment and there's a stream encipherment. In the block, we divide the data in blocks and we send it. In a stream, we encrypt bit by bit. We'll see all of that. All right, clear? All right, so what we do, we have the n-bit plain text, right in here, block of data, and we encrypt it. It will be encrypted with a shared key between the sender and the receiver, okay, the same key, and it will be transmitted. When we receive the data, encrypted data, it will be decrypted with the similar key, and the receiver will have it. All right. So there's two issues here. What we have in here? We have data, plain text. We have key, shared key. We have algorithm, which is shared algorithm, and we have ciphertext. Four things. All right. What is public? What is public in here? What is known? The algorithm is known. Okay. What is hidden? The key is hidden. The plain text supposedly to be hidden, and the ciphertext is hidden. Okay, or the meaning of the ciphertext, right? Actually, the ciphertext is not hidden because it will be transmitted in here. So everybody will be able to get the ciphertext, but will not be able to decrypt it, to get the data from it, right? So Kirchhoff's law, what does it say? We studied Kirchhoff's law last class.
The algorithm is not hidden.
We don't hide the algorithm. The algorithm is shared. Everybody knows the algorithm. What we hide? The key. The key. All right, so let's take example in here. How many padding? So what to create a block? Let's say we have like, let's say that we're gonna create a block of 12 bits. Okay, but I have 30 bits in here. So 12 plus 12? 24. Okay, 12 plus 12. Okay, how many remaining of the 30? 6. So what I have to do with the 6 to create a block? I have to pad it. I have to add dummy bits for it, call it padding, right? Because each block has to be a fixed size before I encrypt it. So we have to do padding. So how many padding bits must be added to a message of 100 characters? 100 characters means how many bits? 800 bits, because each character is 8 bits, 800 bits. If 8-bit ASCII is used to encoding the block cipher, and the block size is 64. So 800, okay, we need to send we have to divide it to 64, plus 64, plus 64, plus 64, plus 64. The last one, it could be less than 64. What should I do with it? Padded, add bits for it. So how you calculate that? Very simple. M, which is the message, plus the pad, modulo 64 how much should be? 0. There is no remainder, right? 0. So what I do math. I move the pad to the other side. The message to this side. So how much the message side? 800 bit. So the pad equals minus 800 mod 64. Just I do the math operation. How much it will be? 32. What?
32.
So how much the pad will be? So how much remaining? 32. I have to bring the 32 to be 64. So how many I have to add?
32.
That's it. 32. Right? So you have to add 32 to it. Okay? Alright, so that's what the pad, it will be 32. Alright, okay. Clear this point? Why we are doing that? Because we divide the data into equal blocks. It's not necessarily the blocks will be equal. The last block will be short. So what I have to do? Add pad to it. I need just to calculate how many bits I have to add to make it the size of the message. In this example, for example, it was 64 bits. Alright, so there is two techniques to change the data. There is substitution and there is a transposition. Okay, in the modern block cipher, it will be designed using these two boxes. We're going to talk about them. Okay, so to be resistant to exhaustive search attack, a modern block cipher needs to be designed as substitution ciphers more than transposition. We use transposition, but mostly it has to be substitution. Let's take example in here. Alright, so let's take this example in here. It says, suppose that we have a block cipher where n equals 64. So what's the block size here? 64 bits. If there are 10 ones in the ciphertext, how many trial and error tests does Eve need to do to recover the plain text from the intercepted ciphertext in each of the following cases? So we have 64 bits, only 1 bits are ones, the rest are zeros. But the ones could be anywhere, right? The ones could be anywhere. So if I have, for example, a block of 64 bits, a block of 64 bits, right? Alright? So it could be 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 0, 0, 0, 1, until the end, 64. The total number of ones, okay, 10 ones, and they are distributed anywhere. Anywhere there. So if you need to figure it out, you have to look at all the options where you can build a block of 64 bits, but there is only 10 ones. All right. So if you are using substitution box, okay, in the first case, Eve has no idea how many ones are in the plain text. Eve needs to try all the possibilities, because in substitution box you don't know how the plain text how many ones it has. All right. So how many you have to try? You have to try 2 to the power 64 twice. Because you could form how many different words from 64 bits? 2 to the power 64. This would need like 100 years to do it by computer. It needs a lot of time to do it. In the second case, where you use a transposition, okay, in the second case, Eve knows that there are exactly 10 ones in the plain text. Why? Because in substitution, you always could substitute 0 with 1 and 1 with 0. Alright? Substitution you could change. But the transposition, what you do, you change just the location. So if the plain text has 10 ones, the cipher has how many ones? 10 also. But in the substitution, you could have like 20 ones in the plain text, and in the ciphertext you could have 30 or 40 because bits are changing. Right? Transposition, we are changing the location. Right? In the substitution, you could change any bit value. So what are the options in the first one in here? Is 2 to power. Okay. How about in here? So it can only search for only the exclusive bits that has 10 bits. Okay, which is much more faster. Much more faster than the previous one. So block ciphers and permutation groups. In a modern block cipher, is a modern block cipher is a group? You know what's a group? We studied groups and fields and all of that last time, right? That's why we studied fields and groups, to come to this point, right? So full-size key transposition block ciphers. In a full-size key transposition cipher, we need to have n exclamation possible keys. So the key should be log 2n exclamation bits. So this is in the transposition. Let's take example. So show the model and the set of permutation table for a 3-bit block transposition cipher with the block size is 3 bits. So the set of permutation table is 3 exclamation. That's what we said. 3 exclamation. So what are, if you have 3 bits, what are the options? You're gonna have 3 exclamation, which is 3 times 2 times 1, which is 6 elements. Okay, let's take a look in here. So so if you have the 3, what are the options to? Okay, so you could have 1, 2, 3, 1, 3, 2, 2, 1, 3. So how many elements we have in here? 6 different elements. 6 different combinations, right? 6 different elements. So if you have a block cipher which has 3 bits, okay, and that's the output, you could have the set of permutation is like 3 exclamation 6 elements. Okay? Alright. How about substitution? That's for transposition. How about substitution? So for substitution, if you have a 3-bit block, okay, for example, you have 3 block in here, okay, so you have a decoder in here, 3 times 8, so converts the 3 to 3 and 8 object permutation using a key of 16, okay, and then you have encoder. So how many options you're gonna have? It will equal, because the 3 is converted to 8, you will have 8 exclamation will be like 40,320 elements, different elements. So usually substitution will give you much more elements, much more confusion, okay, when you convert the plain text to a ciphertext. That's why substitution is the most eminent, the most important part of any cryptography. Alright? So, where am I? Oh, here. Okay. So it's so how many? how many bits you need to model the permutation, 16 bits. If you do log 2 for this number, will give you 16 bits. Alright, so that's what we concluded here. The full size key n-bit transposition cipher or a substitution block cipher can be modeled as a permutation, but their key size are different. The transposition, the key size is log 2 for n explanation bit long. It will be much more shorter than substitution, which is log 2 to power n explanation. Alright? So, now, for the modern block ciphers normally are keyed substitution, or key substitution. There's a key. Okay, key substitution. We'll see it in a second. Okay. So for example, we have like P boxes, which is P boxes, permutation boxes. It's parallel to traditional transposition. What's the transposition? Bit in the input will be input 1, for example, becomes input 4 or 5 or 6. You change the output of it. So let's take a box in here. So 3 types of P boxes. Okay. The first one is straight box. So the number of inputs, how many? 5. The number of outputs, how many? 5. But 1 went to 4, 2 went to 1, 3 went to 5, so on and so forth. So the number of inputs equals to the number of outputs. Okay? We call this straight box, straight P box. In here, what we call it, compression. You have 1, 2, 3, 5 inputs, and you have 3 outputs. So we're gonna lose the value of 2 and 4. Okay? And then here what we have, expansion, B box. So we have 3 inputs. So 1, for example, as input, the input number 1, the pin number 1, went to the output 1 and output 4. Bottom line, we have 3 input pins, and we have how many output pins? 5. So we call this a straight P box, we call this compression P box, and we call this expansion P box. Okay? We're gonna see next chapter how we use all of these boxes. Okay. So let's take example in here. Figure 5.5, which is this one, shows all 6 possible mapping of a 3 to 3 P box. So this is what? A straight box. All the possible. So it could be straight. So how many, when you have 3 bits, how many options you have?
6.
6, right? We already learned that. 6. So these are all the 6 possible options for P box. Okay. So this is a straight P box example of permutation table for a straight P box. How many bits is this? Maybe 64? No. So this is like a 64 bands, right? I think it's a 64. And this is a keyless, okay? So in the output at pin 1, what you get, where is going to come from? Pin 58. So output pin 50 gonna come from where? This is the output pin number 2. It's coming from where? From 50. You're right. Okay. This is in here output pin number 64 coming from where?
7.
Input 07 or input 7. So this is an example of permutation table. So when you talk about permutation table, usually it's like software implementation, right? But when you talk about like boxes like that, it could be a hardware implementation, right? So, um, so in here it says example design an 8 times 8 permutation table for a straight P box that moves the two middle bits, bit 4 and 5, in the input word to the two ends. So 4 and 5 4 becomes in the output number 1 and 5 becomes number 8, and there is shift, right? Will be shift, right? All right. So for example, we need a straight P box with a table. For example, y the 4 is moved where to number 1, and 5 moved where number 8, and then you have 1, 2, 3, 6, 7. So that's the input, that's the output, and the input will be 1, 2, 3, 4, 5, 6, 7, 8. All right. So the relative positions of inputs bit 1, 2, 3, 6, and 8 have not been changed, but the first output takes the fourth input, and the eighth output takes the fifth input. Okay? Clear? I mean, that's very simple example, right? How to create a P box, straight P box. Okay? And this is substitution. Is it a substitution box? Or a transposition? Transposition, right? It's a transposition box, not substitution. But we did not get to substitution yet. We're talking about transposition, right? Look at this in here. A compression P box is a P box with N inputs and M outputs, where M is smaller than N. Compression. You compress it. Okay? So for example, okay, this is example for 32 times 24 permutation. So this is the output. This is the output. So pin number, output number 1 is coming from where? From input 1. Okay. How about 12? Lost. It's gone. We don't.
No,
12 is there.
Is there?
You need 29.
Yeah, 12 is there. How about 15? It's not there, right? Lost. So how many outputs we're gonna lose in here? How many inputs we're gonna lose? 8. Okay. Compression. Okay. Is this a problem when you lose some inputs? Of course, because you cannot figure them again, right? So, but we'll see how we use them later. Okay. So let's take it like studying blocks, topics in here. So in here, that's example of 13 times 24 permutation table for compression P box. Yeah, same as here. Okay. An expansion box is a P box with N inputs and M outputs. So what do you notice in here? So some inputs are repeated multiple times, right? Okay, 0, 3, and 0, 3. Okay. So, all right. So the question now: invertibility. Can we invert a straight box?
Yes.
Yes, because the number of inputs equals to the number of outputs. How about compression box? No. How about expansion box? No. Okay, or at least for expansion box, not definite, but absolutely for input box, compression box, you cannot, because you lost data, right? For the expansion box, you have duplicate data, so it will be very hard to be determined about how to invert it, right? You agree? So maybe we have examples. Let's take a look in here. So figure 5.6, which is this, shows how to invert a permutation table represented as a one-dimensional table. So what you have to do in here, this is the original table, okay? 6, 3, 4, 5, 2, 1. That's the rule. Okay? Then you add the indices to it. 1, 2, 3, 4, 5, 6. Then after that, you swap the content. So The NTCs will go inside the box and this go out, swap them out, okay? So in here, for example, the 6 is inside the box, the 1 is outside. The 1 became inside this, you swap, right? Then you sort. Then that will be the inverted table. So that means if I'm using this block in encryption, I have to use this block where? In decryption. Alright? So if I'm using one box while I'm encrypting, I have to use the inverted box while I am decrypting. And that's how you build the decryption box. That's the encryption box, that's the decryption box. Yes?
Can you please explain the sorting? I sort the last,
Here,
sorting.
just you see, look in here. So what you have to sort these 6, 3. So you start with 1. Put 1 with the 6. Then 2 with the 5. 2 with the 5. 3 with the 2. 3 with the 2. 4 with the 3. 4 with the 3. 5 with the 4. 5 with the 4. 6 with the 1. 6 with the 3. We sorted it. Just. Alright? Then that will be the output box. Alright? So remember that whenever we do encryption, whatever we do in the encryption, what we have to do, the inversion in the decryption. So B boxes, we could build inverters for that. Okay, compression and expansion B boxes are not non-invertible. So look at this compression. 2 is lost. How can I invert it back? I have no data. I lose the data. How can I invert it back? Cannot invert back. How about the expansion? So 1 went to 1 and 2, right? So 1 now, is it 1 or 2? It's not determined, so you cannot invert it for sure, right? Aha. So let's talk about S box, substitution box. Substitution box can be thought of as a miniature substitution cipher. So S box is an M times N substitution unit, where M and N are not necessarily the same. So look in here. So for S box with 3 inputs and 2 outputs. There's a substitution box with the 3 inputs and 2 outputs. So what are the inputs? X1, X2, X3. What are the outputs? Y1 and Y2. So for Y1, I'm using this formula. What I do with it, I XOR X1 with X2 with X3. Alright? And for Y2, what I'm doing X1 only. That's why there is no guarantee that the input will have the same number of ones as the output, because it's not a transposition, it's substitution. We're changing the whole values, right? So the S box is linear because we could build it like this. So Y1 equals, so what we do in here, the Y1 equals 1 times X1 plus 1 times X2, 1 times X3. That will give you Y1. Y2 will equal, the matrices multiplication, very simple, right? Multiply rows with columns, right? You multiply here 1 times the X1, 0 times X2, 0 times, will give you X1. Okay? Alright? So in substitution, what we're trying to do, we're trying to create formulas, operation, complex operation, that the sender and the receiver in the algorithm will agree on. Right? So this is Y1, Y2. If I need to calculate the inverter, I need to calculate the X1, X2. What should I do? Multiply Y1 by 2 by the inverse of this will give you the X1, X2, X3. You agree? The inverse. Right? Okay. Simple matrices, right? Look at this S box with the 3 inputs and 2 outputs. So Y1 equals to what? X1 to the power of 3 plus X2. y2 equals x1 power plus x1, x2. So what's the difference between this and this? This is not linear. It's non-linear operations, right? Non-linear operation. So in here we have multiplication and addition. Okay. So let's take a look at this one. The following table defines the input-output relationship for S box of size 2 times 3. So in here, the input is 3 bits, 0, 0, 0. So this is the leftmost bit, and this is the other 2 bits. Okay, then here 0, 0, 1, and so on and so forth, right? So these are the rightmost bits, and this is the leftmost bit in here. All right? So this is a compression, right? This is a compression, right? You agree? So every 3 bits we convert them to 2 bits, right? So if I tell you, for example, what is the output? What is the encryption for 1, 0, 0? Can we get it from the table?
0,
1,
0.
1, 0, 0, which is 0, 1. It will be 0, 1, right? 1, here, 1, 0, 0, right? It will be 1, 0. 1, 0. I'm sorry. It will be 1, 0. Alright? So based on the table, an input of 1, for example, 0, 1, 0, 0, 1, 0, it will give you 1, 0, 1, 0 will give you 0, 1. Okay? Of course, you could write a decryption box for this. So decryption box for this. How you write the decryption box? 0, 0 will be the output as what? So you're gonna write it like this, for example. Okay. Maybe you're gonna write it like that. Okay, like that. 0, 1, 0, 1. Maybe something like that, right? So for 0, 0, for 0, 0, when you receive 0, 0, it will be what? Okay, it will be what? There's 2 options here. It could be 0, 0, 0, 0, or it could be 1, 0, 0, right? So how can we write it? Right?
You have 2 options. So
Yeah, how can you write it? With 2 options. So maybe this is not inverted, not invertible, because it's a compression. We'll see. Alright? So an S-box may or may not be invertible. In an invertible S-box, the number of input bits should be the same as the number of outputs. Okay? We tried it. It's not invertible. Okay? Let's take a look at this example. It shows an example of an invertible S-box. For example, if the input to the left box is 0, 0, 1, 0, the input in the 0, 0, 1. What is 0, 0, 0, 1? Here. 0, 0, 1, 0, 1, right? Right? So the output is 1, 0, 1 here, right? Okay, let's try the other way. Okay, the output, okay, 1, 0, 1. Where is 1? 1, 0, 1 gave you what? 0, 0, 1 here, right? So why we're able to make it invertible? Because the input equals to the output, right? The input equals to the output. But if so, that's kind of straight box, right? If it's not, it will be very hard to do. All right, the third, so far what components we have learned? Transposition, okay, boxes, and substitution boxes. And they could all be what? Straight, shrink, and expansion. We're gonna come to the third important component that we use in encryption, modern encryption, which is XOR.
Professor, in previous, like, how did we get the output for that inversion, like 0, 0, 1?
Here, this one.
Yes.
So this is the encryption. This is the decryption. Let's take any example you want. Okay. So let's take here very easy. 0, 0, 0 will give
0,
you
1, 0.
0, 1. So now I have to look in that table what? 0, 1, 1. 0, 1, 1 gave you
Okay.
0, 0, 0. Okay.
Thank
So,
you.
how do we create the decryption table? Because it seems very different from the encryption.
This is the encryption, and this is the decryption.
Yeah, I'm saying, how do we create the table? It's given.
Very simple. You're gonna encrypt how many bits? 3 bits, right? So you put 1 bit in here, 2 bits in here. When you receive the bits, how many are you gonna receive? 3. You put them here and here. Look at here and build it. So let's pretend this is not here. It's not here. So 0, 0, 0. Where do we find the 0, 0, 0?
1, 0.
Here. So what should be the output?
1, 0, 0.
1, 0, 0. I put 1, 0, 0. Just, simple, right? Okay. Guys, they get? Yeah. Alright. This is the very important component in any encryption, modern XOR. So it's very important to know XOR, how it works. So XOR, the nice thing about XOR is self-invertible. So as long as you fix one parameter, which is the key, you could go this way or this way. K XOR with X will give you Y. K XOR with Y will give you X. Self-invertible. Very easy. Alright, you don't have to worry about this. So an important component in most of block ciphers is the XOR operation, as we discussed in chapter 4. Addition and subtraction operation in GF2 to the power n field are performed by a single operation called exclusive OR. The 5 properties of exclusive OR operation in the G2n field are there. So there's a closure, you know what's a closure? Associativity, commutativity, existence of identity, and existence of inversion. That's great. Alright? So, alright. So, invertibility of the exclusive OR, it's clear in here, it's invertible. So, then we come to a circular shift. One more component we use is a circular shift. So far, what we learned about substitution boxes, transposition boxes, and XOR. Okay, now we're going to learn about circular shift. What is circular shift? Yes, shift register. I'm sure you have learned it in your digital design. So another component is the circular shift. So for example, in here, before shifting, we have P0, B1, B2, and 2P7, right? Bit 7, right? So let's say that I'm going to shift to 3 bits. So when you shift, I'm going to shift, I'm going to have shift, right shift, in this case, right shift, okay? What will happen, this is our left shift actually. So B0, it will shift 3 times in here, and this will go back here, like circulate, and becomes B7, B6, B5. Circular shift. Okay, think about like a circle. Okay, and in here, this is like left shift. This is kind of right shift in here. Okay, so this component is also used a lot in modern encryption. There is also swap. So you could divide the data into 2 parts, like, okay. So in here, for example, B0 to B7, we swap the first half here and the second half here and here, okay? That's called swap. That's the fifth component that we're gonna use in the modern, okay? Also, there is something called split and combine. Split and combine. So you put the split, you know, the bits in here, okay? And then you combine them in the decryption. You combine them in the decryption. So in the encryption you split, and in the decryption you combine. Okay? So Shannon introduced the concept of a product cipher. A product cipher is a complex cipher combining substitution, permutation, and other components discussed in the previous sections. So what is the definition of product cipher? A cipher algorithm that includes many components. And we have mentioned so far 5 components. What are the components we mentioned? Substitution, transposition, exclusive OR, shift registers, or circular shift, and split, and
Split combine.
divide and combine. 6 maybe, right? All of these, all right? And by the way, when you look at the modern algorithms, you'll see most of them are used. Okay, just we have to have a map for it. Okay, so what you're trying to achieve, 2 things. The first thing is diffusion. Number 2 is confusion. Diffusion and confusion. And you have to understand the difference. So the idea of diffusion is to hide the relationship between the ciphertext and the plaintext. That means if you have the ciphertext, you cannot figure out what is the plaintext. So what you are hiding in here? The relationship between the two completely. Alright? So diffusion hides the relationship between the ciphertext and the plaintext. Clear? Confusion, the idea of confusion is to hide the relationship between the ciphertext and the key. Me as a cryptanalyst is what I have. I have the ciphertext. Either I try to get the key, or I try to get a plaintext. Which one is better to get? The key, because you can get any plaintext later, right? So in the confusion, we need to hide this relation. So confusion hides the relationship between ciphertext and the key. You cannot know the key from the ciphertext. Okay? These are the 2 things that we need to achieve. We create, to achieve diffusion and confusion, we create multiple rounds, not 1 round of operation. So it could be 16 rounds. Alright? So diffusion and confusion can be achieved using iterated product cipher, where each iteration is a combination of S boxes, P boxes, and other compounds. You will see it clearly next class when we discuss about this algorithm. You will see exactly how we use the rounds and how each round has many of these boxes. Alright? But, okay, so look at in here. So this is a product cipher, okay, made of 2 rounds only. This has 16 rounds. This is not a real one. This is just an example. Look at here what you have. So you have 8-bit plaintext. So what is the size of plaintext? 8-bit. And thus, what is the size of plaintext? 64-bit. Okay, here's just an example, right? So in here, it's gonna go to the whitener, which is key mixer. So you're gonna have a key. Usually you have a key. When you have a sender and receiver, you have 1 key. From this key, you're gonna generate many keys equal to the number of rounds, because every round will use different key. But it's generated from where? From 1 key. Alright? So for example, if I have a communication between sender and receiver, alright? So they have to share a key. If I'm using algorithm that has 16 rounds, we will generate from 1 key, how many keys? Key 1, key 2, up to key 16. Alright? So, sender and receiver do not need to know the sub keys. They need only to know the major key and keep it secret. Keep it secret, right? So from that key in here, from that key, the round key, okay, we're gonna generate many keys equal to the number of rounds. In our example in here, how many rounds we have? 2 rounds. So we have key 1 and key 2. Good so far? Good. So we have a plain text. Usually we start with a plain text. We'll end with ciphertext. Where? At here what? Encryption. This is encryption. So you're gonna go to key mixer. So what you do, so usually this is like 8 bits, and the key 8 bits. So what will happen? It will be XORed together. So the first bit of the key will be XORed with the key 1, with the plain text 1, 2 with 2, 3 with 3. So that we call it whitener, key mixer. Key mixer. And then what you divide the data into S boxes. So if the size of the box is 2 bits, how many S boxes I need? How many? 4. So that's what I did. I created. And that's what we call them, substitution boxes. Okay? Then we have a P box. What is this P box? Transposition. You see? Like shift all of these. Okay, what I get in the middle, output of round 1, what I get? 8-bit middle text. Mixed up. Mixed where? Mixed with the key in here, mixed in the S boxes, and mixed in the P boxes. That's the. So this middle plain text or middle text becomes the input for the second round. So it's gonna go to the whitener, it's gonna go to the S boxes, it's gonna go to the P box, and we're gonna get the ciphertext. So what we did in here, it's like, you have a blender, you put banana, you put apple, you put orange, you put watermelon, you put all the fruits, and you press the button, you blend it together. Blended all the fruits together. Now if I give you this mix, until you give me the banana, can you give the banana? If I tell you give me the apple, can you get the apple out of this juice? No, here we can. Here the data is mixed completely, the bits completely, they look completely different. So that plain text, if you look at the plain text, okay, to the output, it's completely different. You cannot even relate anything to anything, right? And that's why we have 16 rounds even, not round, right? Okay. However, okay, why we are able to get the bananas and get the orange? Because we know how to invert this on the other side. We know how to invert this. We know how to invert this. We know how to invert that up to all the way. So we're gonna go with inversion. So it's a very important, whatever we do, all the boxes we have, they have to be what? Invertible. Okay? Your question?
Yes. So the key we are using here, key 1 and key 2, they must be different keys, or they are
Different keys.
both the keys.
Sure. So at the decryption, we're gonna have the same key. They will be able to generate the same keys again.
No, my question is K1 and K2, they
Yeah.
are gonna be same or they're
Different.
Different.
But this is at the sender side, right?
Hmm.
The receiver side will be able to generate K1 and K2 from the key.
So is this something similar to what you use in software that have key?
What?
Do they use this in software that have key? For example, like maybe you buy a antivirus, and the antivirus comes with a specific key that you need to input so that you're able to authenticate.
This is a completely different thing.
It's different from this.
It's a completely different thing. This is a key. Key is like a key, 64-bit or whatever. Okay? So look in here, we said the blending, right? Look at the blending. We start from here, plain text, right? Then it was XORed with 8 bits. You're gonna have, we gave you S box 4, you see in here? So 7 moved to here, 8 moved to here. Then you have 2 and 4. Then came as unmixed. So basically, the bit, any bit, it was mangled and played with every input. Either in the S box or the P box or the key level, or all of that. Alright? So you cannot even, so if you look at the output in here, the one here, it basically went through too much, it's mixed too much, right? All right. So two classes of product ciphers in general. There is FECL cipher and non-FECL cipher. We'll tell you what's the difference. So modern block ciphers are FECL. This is example DES, DES. You know what's DES, right? DES is from the first kind, FECL. ES from the second time. Okay, this is FECL. Okay, this is non-FECL. Okay, all right. So we're gonna cover all of that as we go. So let's tell you the difference. In the FECL cipher, FECL designed a very intelligent and interesting cipher that has been used for decades. A FECL cipher can have three types of components: self-invertible, invertible, and non-invertible. Self-invertible is like what? XOR. Invertible like what? P-box, straight P-box. Non-invertible like? Okay, that's what it is. So it could use the different boxes. For non-FECL, it used only invertible boxes. Okay? So in here, for example, okay, the first thought in FECL cipher, you have a plain text. So in here, mixer. The mixer is self-invertible because you do, okay, then you do the encryption. The same thing, you go back, we're gonna use the inverter. So diffusion hides the relationship between the ciphertext and the plain text. All right. So what is this example? Okay. This is a trivial example. The plain text and the ciphertext are each 4-bit ones, and the key is 3-bit low. So plain text is 4 bits, cipher is 4 bits, the key is 3 bits. Okay, assume that function takes the first and third bits of the key. It takes the key has 3 bits. You take the first and the last only. And interprets these 2 bits as a decimal number. Convert them to a decimal. So 1 would be 3, right? Convert them, the first bit, third bit, combine them together, convert them to decimal. So let's say that the key I have to throw this away. Okay, so let's say it's 101. So what we're saying here, take the first and the last. What's the first and last? 1. This equals to 3, right? All right. So okay. 2 bits a decimal number, square the number, and interprets the result as a 4-bit binary pattern. So square it will become 9. Okay. So if you need to convert it as a binary, 1001. Right? Right? You see the sequence, right? Okay. Show the results of the encryption and decryption if the original plain text is 01111 and the key is 011. Very simple. So 011, it will be 3 squared 9. It will be 10. So that's what we did actually. So plain text with the function of k. 0111, that's given to us somewhere here. And then 1001 is what we got in here. The function, right? Right? XOR then gave you this. The decryption, you're gonna do the same thing. So you're gonna use the same key. The key is not, it's not used as it is, it's calculated. There is a function, there is a rule. Agreed up on between the sender and the receiver. Anybody's confused yet? Confused?
Yeah, can you do it again?
Do it again, no problem. So the rule says that, okay, forget about this, look in here. Okay. The rule says the plain text is how much? 0, 1, 1, 1. The key is how much?
101.
1, 0, 1. The cyber how much? We don't know. Okay, the algorithm, what is the algorithm? C equals P XOR function
Okay.
of K. Right? So what are, this is given, given, given. This is we need to find out. Right? So the rule says how that function works, how this works in here. It says, take the first and the last, combine them together. What is the first and last? 1, 1. Then it says, convert it to decimal. What is this in decimal? 3. Then it says, square it. What's the square of this? 9. Then it says, convert it to binary. What's a binary of 9? 1, 0, 0, 1. So now I know what? This one. So let's do it. So what is the plain text? 0, 1, 1, 1. XOR how much? 1, 0, 0, 1. In XOR what we do? If we are the same, 0. Okay, 1 and 1, 0. 0 and 1, 1. 0 and 1, 1. 1 and 0, 1. You got it? Yeah. Now, after that, you have to do decryption. The same thing. Decryption. In decryption, what you do? You need to get the plain text, right? So you have the cipher. How much is the cipher? Here. It's all with the same function. Okay, and you get the result. All right? So there is a function that both parties need to agree upon. Okay, to generate the key. All right? It's not as simple as this. It's just an example. Okay, it's not as simple. It's much more complex than that. All right. So improvement on the previous feature. So to improve it more, instead of having all the whole data goes like this, we use split. Okay, so what we do, we divide the data into left and right, split them, right? And we apply the key on the right and we pass the left here. So we don't apply the key on the whole data, we apply it in half of it. Okay, we pass it in here. And in the decryption, what we do? Did we do anything with this? We pass it. We didn't do. So what we did in here, okay, we have the right side passed directly. You see, all the way. However, to make it more complex, we took the right side, okay, and we did the function for the right side with the key, and the output we XORed with the left side. We try to complicate, we're trying to get cryptanalysis crazy. We cannot figure it out, right? So the R, we did not do anything best, okay? However, what we did, we applied the function for the right side, then we XORed it with the left side, and we passed to L2. So now we reverse the operation. So this side, did we do anything?
No.
We passed as it is. Right?
Yeah.
For this, what we have to do, we do the same thing. We apply this, you know, we do the right side, we do the K with the received here, and then we XOR it with the L and with the best plot. So you have to make sure what you do in the right side is inverting or reversing the left side.
Sir?
Yes.
Oh, are we always going to go from the, as in, is the right going to always be free, or we can switch it or not?
You what?
Can we do apply the function to the right side and let the left go?
Sure, you could do that. That's by agreement. That's a protocol or algorithm we're gonna write, right? But this is only one round. It does not apply only like this, just simplistic. Usually we said we have many rounds. You know what will happen in the sixth round? They switch. They bring this in here, and they bring this here, and then they do it again. to make it more complex, right? In here, yeah, it's in here. So you see in here, they split the data in right and left. They did the same thing, we call it mixer. And you know, the left side becomes what? Right side. And the right side becomes the left side. And then it goes to second route, and then you mix them again, So look what you did. You divide the data, you applied to half of it, you XORed with the other half, you switched, okay, and then you did multiple rounds and all of that. It's like you really truly blending it very well. Okay? Okay, non-feasible ciphers use only invertible components, a component in the encryption cipher has the corresponding component on them. So this has only components, right? However, feasible what has self-invertible, invertible, non-invertible boxes. Alright? So attacks on block ciphers, attacks on the traditional ciphers can also be used on a modern block ciphers, but today's block ciphers resist most of the attacks. Okay? So what kind of attacks we could have? We could have differential cryptanalysis. Okay? So for example, Eli, Beham, I think, and Adi Shamir introduced the idea of differential cryptanalysis. This is a chosen plain text attack. We already explained what's a chosen plain text. You start with a plain text, you know. Okay. So in here, for example, assume that the cipher is made only of one exclusive OR. Very simple. Self-invertible, right? Okay. Operation as shown in the figure. So in here you have plain text, you XOR it with a key, you get C. C, you XOR it with a key, you get the plain text. Or in here, for example, you have C1 with a plain text 1 with the K and C. So you have two ciphers. You have two ciphers. Okay. So if you have two ciphers, what you could do, if you XOR, look at this. If you XOR C1 with C2, all right. I mean, you are a cryptanalysis. You are watching a communication. You come up with two C's, two ciphers. Possible, right? You cannot read them yet, right? So you receive C1 and C2, XOR them together. So C1 equals to plain text 1 XORed with K. You put it here. And this equals to P2 XORed with K. Put them in here. When you do the operation, what happens with the K and the K? They cancel each other. Similar things. So what you end up with? P1 equals the, okay. So you end up with plain text XORed with P1. So you could do further analysis that we call differential analysis. So you'll be able to find that. So we add one S box to the model here. So in here, we're gonna add one S box. Okay. So we add one more S box as shown. So as you see in here, this is the plain text, and this is the output of the self-invertible XORed. Okay, and we have shrinking S box, so it's converted from 3 to 2, and that's the rules. So X 3 bits, because here will give you 3 bits, right? You're XORing 3 bits with 3 bits will give you 3 bits. 3 bits, and this is the output. So converts the 3 bits to 2 bits. A shrink P box, right? A shrink box, right? Clear? Lost? Did I lose any of you? Okay. At the end of the lecture, after 1 hour, I lose myself. So it's not, I understand I could lose some of you. So just stop me if you're lost. All right. So what you do in here, Eve now can create a probabilistic relationship as shown in the table. So the probabilistic is, see, this is a table. Okay, if the plain text, okay, XORing the plain text together give you 0, 0, 0. Okay, what is the chance that C1 XOR C2 equals 0, 0? It's like 8 out of 8. So like 100%, because you're gonna receive a lot of what? Cybertext. So let's say you received 100 ciphertexts. You take C1, C2, C3, C4, C5. You try to create statistics, differential. You look at here, for example, if the XORing P1 and P2 give you 001, and the ciphertext, okay, the ciphertext here will be 2 chances, 4 chances. So this is like 50%, 25%, 24%. You're trying to create what? Analysis. Is the class over? What time class is over?
45. 45 should be over. Yes.
It's over? Okay, just a few seconds, we'll be done, okay? So you're trying to create analysis for that. So you create, like, you see in here, 8 out of 8 becomes like 100% in here, right? All right? So you're trying, you got the idea. So you're trying to create some analysis of the data, okay, and that will help you to detect the data. There is linear cryptanalysis. You could take a look. That's easy. I'll keep it for you. Okay. Then at the end, we're gonna talk about modern stream ciphers. Okay. There is synchronous stream ciphers and non-synchronous stream ciphers. Okay. So in the stream ciphers, the data before we were talking about what? Block ciphers. We divide the data into blocks. In here, no. We take it bit by bit. So bit 1 or plain text, piece 1 with key 1, P2 with key 2, and it's like ongoing, like, one by one. So in the modern stream cipher, each R-bit word in the plain text stream is enciphered using R-bit word in the key stream to create the corresponding R-bit word, okay? So that's exactly what will happen, okay? So it will be encrypted one by one, okay? We're gonna take examples later in later chapters about real protocols for cyber. Okay, so I'll keep the rest of it to take. The last thing it talks about feedback shift registers. Why we need feedback shift register to generate the key? What's the problem in here? When you look in here, how to generate the keys, right? So for generating the keys, we use a feedback shift register like this. So it starts with a seed, and for every new bit there is a shift. Then you have a new key, and so on and so forth, right? So you could generate many keys from this until it repeats itself. Okay, so you could take a look at that. It's very easy. Thank you.